Search, relevance, content selection, recommendation engines. The new episode. So we're going to focus on the common part of these four, and there are a few standardized steps, which I can loosely group here. Indexing is about how do you store the documents and retrieve them. Retrieval, separate step, but I think it's part of indexing logically from a system design perspective. It's how do you create the initial set of documents. From a huge index, pick those few hundred of thousand, maybe tens of thousands, to select the final search results from, search or relevance or whatever results from. Ranking is where the machine learning part happens. We're also going to cover how to best implement these things in the real world, and some specifics related to each individual sub-problem. So the indexing phase, it actually applies to all content retrieval and ranking problems. This bold italics, content retrieval and ranking, this was actually one of the titles, one of the working titles. I figured it's less informative than the one I used, but honestly, in my head, search, recommendations, newsfeed ranking, personalization, content retrieval ranking is all in the same realm. So in the vast majority of product use cases, your thought process would be almost identical at the beginning. When it comes to search indexing, I mean, of course, if you've been asked to design a search engine like Google, indexing begins by crawling the content you need to index, like the web. But to be honest, there's really not much difference from the system design perspective, because, well, if you build in an index, a search index for the whole world, you need to crawl the web. If you build in a search index for your own company, you kind of have the documents internally. So what? It's just one component. Building a web crawler is a standard-ish task. It's not rocket science to build a web crawler. So logically, again, it sounds like a huge difference whether you already have the data to search and index and rank upon, or you don't have this data. But if you don't have the data, you just have a component to obtain this data. What index actually does, I think, for once I'm going to start with functional requirements. What the index actually does is it stores documents and then can return these documents, mention some query. The query doesn't have to be like a textual search query. In fact, that's also important to understand that even if you build in Google, even if you build in a web search engine, there's a huge difference between the query you write, like you type into the search bar, and the query that goes into the index leaves. There's a huge process called query augmentation, query rewrite, or however you call it, which blows out the search space dramatically. So you type like 3 words, which is literally under 100 bytes. The query that goes into the index leaves, will be hundreds of kilobytes. What the index should do, so the index consists of nodes, and it's a requirement. You cannot do it any other way because it has to be absolutely scalable. That's probably the most intensely scaled part of most search and recommender engines. So what usually happens is the search query hits one of the index nodes, and this index nodes this particular node would return you some documents that fit this query. One of the important tricks is that at some point later, once from all the index leaves, you have some documents retrieved, at some point later, you would need to rank these documents. You would need to sort them to present them to the user. Pushing code to data is a lot better than pushing data to code. So in practice, speaking about system design, your index would do a lot more than just retrieve the documents. Your index would probably at least compute some features for these documents. Your index would probably even return the documents in some predetermined order, so that what is returned sooner is more likely to end up in the final search results compared to what would be returned later. That's another separate conversation. And I think last but not least, your index nodes should support data updates, although again, this is not super critical, because in the real life, if you're talking about searching or recommending some data that changes frequently, what your model would look like in the real world, you would have some classifier at the very top, like an intelligent load balancer. And you would, at this level, you would decide what's the query enters your system. You would decide, is it a high frequency query? or is it a like deep search or deep content selection query? Because in practice, the data access requirements for high frequency queries are extremely different from those for the rest of the index. A few interesting factoids, a few interesting funny facts. I cannot claim it because A, I do not know it for a fact, and B, even if I would not disclose it. But from what I understand about the history of large-scale computing on this planet, large-scale consumer computing on this planet, MapReduce was first used at scale specifically to build indexes. So if you're building a huge search engine, you can crawl documents and you have a bunch of hard drives in your university campus room that store the contents of the documents. Now to search these documents, you need to have some index for those documents. So you can look for all the documents that contain certain word. Once you have exhausted your wardrobe space, once you filled it with hard drives, the only way you can perform this index collapse to transpose this matrix, I'll talk about this later, is technically to build something like MapReduce. And I think, like I'm speculating, I cannot know for a fact, and even if I would know, I would not share this. But I think it's plausible to imagine that MapReduce was the result of the thought process of how to optimize this index collapse phase. And again, on a related note, second factoid, log structured merge trees are gaining in popularity as modern NoSQL, not only SQL, databases / key value stores. And it's really interesting to think, at least to me, that the once you have the search index is never stale. It changes over time. Documents get added, changed, removed, and you need to keep updating this index. It's really hard to update the index live. I mean, it's kind of not to say impossible. It's not feasible to keep updating the index on the fly because the index is read a lot more frequently than it's written, and latency requirements, super high speed responses are essential. So what usually happens with index nodes is they're being rewritten. So what you probably have in practice is something like you have this many machines, let's say 1,000 machines. It's a sharded index, and you wouldn't just, once you keep having new content, or once you keep editing content, creating content, edit content, you wouldn't just keep updating these index nodes. You would just rebuild index node like one after another and hot swap them, which is effectively how LevelDB does it, which is effectively how Bigtable does it, and how Spanner does it. So, like, in a way, you can think of the same person, the same people, Jeptin and Sanjay at Google, inventing two things that one builds on top of another. The first one is MapReduce, and the second one is log structured merge trees for databases.
So you mentioned that we can just, so let's say we have a sharded index, and I want to add a new document, a bunch of documents. So they get added to the shards. So in reality, what you're saying is that there is another thread running probably on every shard that is recreating the entire shard and then hot swapping it. Is that what really happens?
I believe so. So, okay. So the cadence of hot swapping, getting into the weeds from slide 1, why not? The cadence of hot swapping is probably in the order of hours. But the fundamental idea from the design perspective, from the system design perspective, is almost indistinguishable for index node updates and for locked structured merge tree node updates. So if you think about how do you update data in like LevelDB, you have a sorted list table in memory on disk where you can quickly get to the right place. If it's an SSD, it's even faster. SIGs are fast. But you have this augmented table in memory, and then once in a while a compaction phase happens. So once in a while you rewrite this smaller table, part of it to the whole table, and replace the old one with a new one. So with updating the search index with a new document, the index node that has to be updated because some words that this node handles are affected by a new document. This index node would eventually be replaced by the node that has this document. But at the same time, you also...
Right. So the thing is, now we are constrained by the fact that the index on a shard needs to fit in memory. Uh, and like if I was reading about Lucene the other day, and it said that Lucene, after some version, they stopped loading the shard in memory. They serve out of SSDs or from disk. So I imagine, I'm wondering how that would work if your shard is too big. Does it require that the shard size be small enough that we can load it in memory?
Uh, I do not believe it's a hard constraint. In fact, I was advocating for this to not be a hard constraint many years ago, and most smart people realized that even before the solid-state disks, SSDs, became widely available, once it became clear they will be available, everybody understood that it's just pointless to store everything in memory because it's so fast to read from an SSD, especially if you can design your data layout on disk so that it's one SIG and then semi-continuous read. With NVRAM, that's even more true today. So yeah, it's a fairly advanced topic, how to design index leaves. I'm fairly positive full in-memory indexes are only useful for a very narrow set of applications. With this being said, I believe that the best design for a large-scale system, since we are talking about this, is a combination of two. So you have this index nodes, index leaves that are fixed in their state. So you hardly update them, you just hot swap them with the new data. And you have, so let's say you have 1,000 machines like this. You also have 20 machines with super fast in-memory index. And a search query goes to both. And then you join the results. You can always deduplicate later. And ultimately, once the document enters the index, you can already search for it. It's just in the first 2 minutes of this document being in the index, it's served by the in-memory index on a smaller cache layer. Ultimately, this cache layer will have to be cleaned up because once the document is properly index collapsed into the right index node, you don't need to use the memory of this intermediate level. That's a similarity between the search index and the log structured merge tree in a stuff like Bigtable. It's a good question, yeah, and I think it's my fault for not putting this into the slides right away. The index does not have to be memory on each index node. It's actually now when I think about it, it's not even clear if the index node leaves are CPU bound or RAM bound. So I believe you can think of an application where one or the other would be true. So that's trickiness at its finest. I think, yeah, actually now when I think about it, what will probably happen is as long as you, the designer of the search index or recommender engine index, as long as you see that your CPU is not really used a lot, you just keep pushing more and more data, more and more code to pre-compute some feature values per document returned from each index node. So as long as you have CPU there, you can use that CPU to free up the CPU of the actual root node that would combine all these results from all the leaves, right? I think it would be better. Yeah, I believe it would be better to use the CPU more because since the index scales well, you can always add nodes if suddenly you use a lot more CPU. You can always add nodes, reshard the data, and your CPU usage would be below the fair, reasonable threshold. So yeah. Let's try to get slightly out of the super complex topics for the time being. Yeah, this was a good detour, thank you. All right, so now retrieval. Index collapse is absolutely batch. Index collapse is like a slow running process that emits new index shards every once in a while. New as in replaceable, hot swappable. The retrieval is absolutely real time. In fact, I honestly believe it's one of the people say that for search and recommender engines, accuracy and relevance and completeness are hard problems. Everything that I know about this industry tells me that performance of those retrieval engines is as complex and as important as retrieval, as the quality of the actual ranking. I'm slightly out of date on this data. I mean, I've not been working in this space for maybe more than 5 years, but back then my instinct and I think overall conclusion was that we already know that once you have enough data collected and enough money to buy more data, we already know that the ranking itself will be good enough. Like Google search ranking is good, Bing search ranking is good. It's not to say it cannot be better, but it's certainly good enough for most intents and purposes in practice. To the degree that, as a business, a big company that runs search at this scale or recommendation at this scale, they would win a lot more by decreasing latency by 10% compared to making their search even more perfect. The marginal utility, like the gain they get from, like, there's like 100% precision metric, right, or whatever metric you use. Once you're here, which is like 30%, there's a long way to go. But once you're really close to this part, you're almost flat. So you don't really improve. So I would go as far as saying that the progress in search engine optimization in terms of system design is probably mostly focused on performance these days, as opposed to ranking. I mean, I could be off. There are different problems, but since we are now at a system design meetup, I think it's more interesting to focus on how to design the system so that we don't introduce unnecessary performance loopholes here. So I mentioned this two-phase lookup system. Two-phase lookup is a bad term. Two-phase retrieval. That index nodes that there are many of those. The way it actually works is pretty simple. Because the index is sharded, and because the shards are independent, let's say you have 1,000 nodes. And let's say your index is, I don't know, a terabyte, a petabyte large, huge. Even if a node contains millions of documents, if you use the simplest possible heuristic to find maybe the most relevant 50 or 100 per node, the chances of you actually getting the right document you need are extremely close to 100%. Because, like, if there's some document that is not found on, let's say, page 1 of Google, I'm going to keep using search as an example, but it applies to relevance 100%. If you have some document that is not found on page 1 but found on page 3, from a huge number of nodes you have, from a huge number of search nodes you have, chances are only 1 or 2 documents per node would make it to the actual search results. Well, in fact, chances are 0 documents per node would make it to the search results. And out of the nodes from which the documents did make it to the actual search results page, the average number would be 1. So what happens is each node would compose a small list of candidate documents and send them upwards to the ultimate ranker. But this number of documents can be small. It's really hard to make a mistake of not sending enough documents. Because again, if you have 100 documents, chances are you don't improve much if you send 200 documents, because most documents that are relevant are in the top few among this list. It's also very easy to check. It's a famous second-order interview question, by the way. How do you know you're doing a good job? How do you know you're returning enough documents? Well, you can just say that for every 100th query. So for 1% of user queries, I'm going to enlarge this number from let's say 100 documents per node to 500 documents per node. This query is going to be 5 times more expensive, or even more than 5 times more expensive, because there is more to re-rank. The latency would be larger, but you can always use your search relevance metrics to see if this actually improves your search results. And trust me, those are smart people. So if this would improve your search results, they would find ways to get those documents quicker. The truth is, this is not the bottleneck. At least it was not the bottleneck when I was doing this. I don't believe this has changed. An important system design trick is, so let's say you have these 1,000 nodes. I'm going to keep using this number. 1,000 index nodes, and you have your search query, you augment it, you send it to all the nodes, you get back the results. If you wait for these results to arrive to your final ranking component, final ranking node, you'd be wasting time. Well, first you have to wait for all the results, right? What if one of them is super slow? Chances are, if within, let's say, some reasonable time frame, I don't know, 50 milliseconds, you only get results from 9,995 machines of this 1,000. Sorry. So if you have 1K machines, if within some 50 milliseconds you get responses from 995, so 5 I have not replied yet, in practice you can just ignore it. Like, you're going to return incomplete results. What are the chances that this one result that you would not return would be super critical? Well, 0.1%. And the other result is probably about as good. So in practice, as I mentioned before, performance is more important than relevance metric here. And since you do want to optimize performance, you can optimize it a lot more by replacing one-time return of all this, however many results come up from each leaf. You can replace the one-time response, request response. You can replace it by a streamed response. And you can optimize your nodes so that once they get the query, as soon as they can, they start sending the documents back. So you don't have to wait for the whole however many milliseconds. The node, the machine that is going to be performing the ultimate ranking, it can start ranking the results, or at least computing features for the results, as soon as those results are available from the index leaf nodes. It sounds advanced, but it's actually pretty simple. I mean, in the modern world where we all speak pub/subs, as opposed to like REST or request responses, it's a good example of a system where you absolutely win by replacing like post or get and then response, like HTTP request. You win a lot by replacing this by a streamed kind of response. Yeah, I think this part we covered. On designing the index, the obvious way to explain this part is to think about a document's index. I honestly believe inverted indexes are still underrated, as in it feels like underrated as in they're not given enough credit in today's world, because it feels like, oh, they can only use text terms for search. Well, yes. Oh, but we would like to search for stuff that is not textual. Well, yes. But we're talking about the lowest level retrieval phase, right? We're talking about how to get the most relevant documents into this filter set where you can ultimately re-rank them. So I'm going to go ahead and make a bold claim that in the majority of search queries, which are not textual, the design is still better off using textual, like word-based indexes. For example, like let's take an extreme example. Let's say you're building a restaurant recommendation system, and let's say you absolutely want to make sure you only return restaurants from within certain geographical area, so a few miles from me, like under 10 minutes drive from me. On the one hand, everybody these days would say, oh, it's a quad tree problem. You need to have a data structure that like partitions the space into some rectangles or whatnot, so that you can only query the restaurants within certain geographical area because it's faster. Absolutely true. But at the same time, I mean, yes, you probably want to use a quad tree for this problem. But at the same time, if you just annotate each restaurant with a bunch of artificial tokens, keywords, associated with this location, to various degrees of granularity, like from a street name and some geocoded location for this particular, well, quad index in your quad tree, all the way up to like city and country, chances are you have a system that is good enough for the users, from the user perspective, especially if you have static ranking. Yeah.
So just to add to that point, that is exactly what Lucene does for geospatial indexing. They will geohash the lat long to like I think they use the N or the Z form, and I think Google uses the S2, which is the Hilbert curve. So that with every document they associate that some sort of a geohash, and that's how they do like search restaurants nearby, and they get the results.
Well, yeah, it's ultimately there's a continuum between exact matches and imprecise matches, and there are two ways to solve it. One is to blow up one way is to use exact matches of the search index terms and blow up the query. The other one is to use exact query matches and blow up the document space. The better solution, of course, is middle in the middle. I have a slide about this, like half a slide about this, with the LSH, locality sensitive hashing, as one of the means to perform index retrieval. So the idea is that you can have, let's say 32 weird functions, each function. So, well, I'm talking about this, so let's talk about this. Think of any domain of search. Think of like book recommendations. Think of searching documents. Think of restaurant suggestions. Consider the following cost function. Consider the following feature vector computation. You take two random points in this space, like two random documents. You compute some similarity between your new document and A and B. These two are A and B. If your document is closer to A, you return 0. If it's to B, you return 1. So your function returns 0, 1. You find random pairs of A, B, absolutely random, with the only property being that approximately half the documents are closer to A and half to B. So it's about 50-50 split. Each of these functions gives you a bit in a search space. Take 32 functions, or 48 functions, or 64 functions, doesn't matter. And you can represent each document as the bit string, as a bit mask. And for most intents and purposes, as long as your functions somehow map to the actual similarity, clearly identical points would map to the same bit mask. Similar points would extremely likely map to similar bit masks, like the same bit mask. And then you could say, hey, you know what? My query would actually be looking for all the binary words that are within, let's say, 3 steps, or within, let's say, 2 steps, 2 bits changed, Hamming distance 2 from my binary word for the query. The way you do 2 steps is made in the middle. You blow up the query space by 1 step, and you blow up the document space by 1 step. And then you look for exact matches here. So even though it sounds like a totally different idea, the ultimate matching function is still the same as for inverted index on words. You blow up both spaces. Each document ends up in multiple locations, but the search query just gives you all the hits. And yeah. Again, slightly more advanced topic. The only point I'm making here is that inverted index as the means to search for documents still takes you places. Mathematically speaking, inverted index is just a transposition of the metrics, like from a document to a list of words. You get to words into a list of documents. Document IDs, of course. You don't copy documents. This is, yes, what MapReduce kind of does behind the scenes. And yeah, that's it for this slide. We kind of covered this so far, LSH hash and Hamming distance. I think the only thing I would add here is that search and recommendation, again, I'm going ahead of myself slides-wise. Search and recommendation, they look very different, but in fact, they are extremely similar. The only difference is, when it comes to search, it's the search query that's the king. And some personalization data about who the user is and what their preferences are is like a nice add-on information. In the world of personalization, recommendations, like feed selection, it's the opposite. There's no search query, or there is some search query. In fact, search query is always there. There's device, there's time of day, there's IP location. Have you changed countries or places? Is it your birthday? Is it raining or not raining? So the search query is always there. It's just implicit. It's just the ranking function, the mathematical cost function, the penalty function of ranking will put a lot more weight on personalized features as opposed to on the actual query you're looking for. But it doesn't change the nature of how you build the index and how you update this index. So yeah, I wanted to mention this LSH hashing. Another clever idea inside of quad trees is you take this fractal line. It goes like this. I probably should find a picture, which I haven't. But then you can like blow this up. So this fractal line covers the whole space, and it has the property of if 2 points are next to each other. So you build this line, and then each cell, each pixel, if you wish, becomes indexed with the index of the step at which you've seen this pixel along the line. And then this index has a property that if 2 dots, if 2 points are close to one another in the Euclidean space, the likelihood of them being close to one another in this unfolded and strengthened out index space are high. So you can just put different fractal nets in different angles, rotations, and starting positions onto the like grid that you need to search over, convert those into query terms, and surprise, you get an index again that works.
What are some of the drawbacks of fractals?
Drawbacks or
Drawbacks of using like fractals like the input curve or the end curve.
Well, it's still probabilistic, right? So first of all, if you want to use the space effectively, like CPU and RAM, quad trees would still win, both on average and on like P99, because when quad trees miss.
In comparison to what? I heard that R trees are better than quad trees as far as space and index updates are concerned. Because with quad trees, you tend to, you can have like an unbalanced tree, and R trees are more balanced.
Okay, I'm no expert right away, but I think quad trees are an umbrella term. You can optimize them in so many ways. Like, you don't have to keep them unbalanced. In fact, you can build a quad tree that perfectly balances itself based on your data points. It's hard to rebuild it, but for a fixed set of points, you can build it this way. It's almost tempted to say it's a matter of preference, because in a way it is. When I don't know the exact answer, I'll give you my umbrella top level answer. The umbrella top level answer is that when you're designing a system, your ultimate goal should not be design a perfect system. It should not be to design a perfect system. Your goal should be to design a system that doesn't fail under predictably growing load. So from the top of my head, it's not clear either of these solutions is best, which kind of means that there's no winner. You would not go horribly wrong whether you pick each of those. I can think that if you need to add places quickly, and the way you add places to this plane tends to be super clustered. Like if you're Yelp and suddenly you add a new location, like a new country, you're going to have a few clusters of big cities there, and within each city you're going to have a few clusters of downtowns. So you probably would like to use a data structure behind the scenes that would not suddenly overload some nodes and not give you like n squared search space, because somehow all the good restaurants and a lot of good restaurants suddenly ended up on the same shard because they're close to one another physically, like Las Vegas Strip. These are the considerations I would think of right away, but you can mitigate them in either solution. So again, no clear winner. All right. Now, once we covered indexing and retrieval, the next step is how do you perform the ranking. Logically, ranking would happen in one place. It doesn't have to be a single physical machine and single CPU core that like single thread that does all the ranking. You probably can optimize this further if you have to. But logically speaking, there are two distinct phases. Phase one, you talk to all your index nodes, index leaves, and you get some documents to choose from. Phase two, you need to select top n and rank top n among these documents. There's an important offline-ish comment to make here. I couldn't find a good way to put it into the slide, so I'll talk about it. It's about the history of using machine learning for relevance and ranking search cost functions. So I think that it's safe to say that as of 2021, most products, most applications would use machine learning at this stage. It's just impossible to find. Either it's a super simple, like a one-man show Craigslist that does some trivial retrieval and that's it, or they use some sophisticated-ish machine learning methods behind the scenes to retrieve the best documents. It makes a lot of sense for all of us right away, because fundamentally optimizing once you want to optimize something, you have a cost function to optimize. Once you have a cost function to optimize, machine learning is the means to optimize this cost function on your data, and it scales for free. You just send it more data, You get more clicks, or you buy human labelers to tell you what are the good search results or good recommendations, and what are not the good search results or search recommendations. And suddenly you get more data, which at some point the volume of this data becomes so large that manually tweaking the numbers becomes implausible, whereas machine learning can just do it for you. I want to make an important point that it was not the case 15 years ago. And it was a huge open debate for a while. Is it even appropriate? Is it even ethical? Is it even safe to use machine learning models for ranking and relevance? I was younger, so I was more like brutal, opinionated, arrogant, stuff like that. So I was always the guy saying, "Why not? That's a natural step." But as I got older, I think I can appreciate more and more the value of thinking against machine learning. Like, full disclosure, today I would of course use machine learning. I'm not saying that we shouldn't, but it's important to understand that if you do use machine learning, you end in the modern day machine learning, like traditional conventional machine learning, especially neural networks, they have this property of being inexplicable. So it does something behind the scenes, does it better and better. You have no idea why does it do it. So a really important and really clever counter argument against machine learning is the following: what if it's a matter of national security, and you have an adversary that has more computation power and better algorithms than you, and suddenly, like, you roll out a new ranking model, I don't know, 2 p.m. on Tuesday, by 5 p.m. Tuesday, certain sites, certain pages, certain recommendations that you believe should not be there are in the top places. If you have some understanding of your model, you can figure out some ways to detect those malicious entities and counter them semi-manually on the fly. But if your model improvement process is all fully automated and you just ship a new machine learning model every few hours, and that entity adjusts every few hours, you're screwed. So the point is, if you have a history of models that have passed some manual validation, worst case scenario, you can go back to the previous model or the previous model, and chances are it's going to work just fine. With machine learning, when you don't have any idea of how it works behind the scenes, you are, in theory, vulnerable to this kind of an attack. I don't believe it's a practically sound argument, but I think it's an important thought experiment to think about. So basically, it's like when you're taking a course in neural networks, you probably can get a passing grade if you design a neural network that runs a nuclear reactor or powers a self-driving car. But if suddenly it fails, you cannot explain the failure mode, it's a good sign you've done something wrong. For self-driving cars, so I mean, the natural conclusion for all of us who live in this world for a while now, the natural conclusion is that you can use advanced machine learning for sub-problems where you kind of know it does better than humans. Like, the self-driving car could probably detect red lights or road marking. It can do it using machine learning a lot better than it would do it using any human-coded rules. Well, the ultimate decision of whether you can go on this red light, on this green light, I would sleep better if there were some human-tuned heuristics at that point. Not because I think humans are better in terms of optimizing the top-level performance metrics of this car, but because I know that if something goes wrong, we don't have to slow down the whole fleet, like to stop the whole fleet of these self-driving cars until they resolve it. We can just change the threshold. Hey, wait, not 0.5 seconds, but 0.7 seconds. And we can keep running until they investigate. That kind of makes me sleep better. And rent. Yeah, so for ranking metrics, this is no longer a secret. They used to be secretive-ish 15 years ago. We can openly talk about many of those. Most search engines publish their mathematical formulas and publish papers to optimize those. I'm pretty familiar with DCG, discounted cumulative gain. It's when you assign weights to each document returned by your search engine. So you imagine if it's a search engine with no personalization, you send the pair of the query and the search result to a human labeler, and you get back a score, let's say from 1 to 5, where 5 is excellent, the best possible result ever, 4 is like okay, good, could be better, and 1 would be terrible, it shouldn't be here. And then your cost function just becomes how many 5s are there in the top of the list. So what you do is you just sum up the scores of the top 10 results but each score goes with the coefficient. The coefficient is like 1.0 for the top result, and it goes down somehow as you go further down, because you want to maximize the chance that 5s go above the 4s and stuff like that. There's tons of research going on in this field, remarkably many papers. At least that used to be the case when I was in the field. Ultimately, again, it's the machine learning problem. You can postulate the problem. You can collect the data. You can measure the result. You can come up with a number that makes sense, and you can find cases where your algorithm can be improved. That's the biggest point of that. Not the machine learning input, but that not only you know that you could do better in terms of improving your metric. You can run a huge A/B test. You can sample random queries from your query stream. You can send them out to human labelers. You can get back the results. And of these, however many queries and however many results, you would say, hey, these are 10 worst offenders. This is where we totally don't do our job well. This is where we lost. This is where we do our job super well. And once you have this process established, you can actually compare two rankers, like the current ranker and some candidate ranker. So you issue tons of queries against your own system. You find the difference on which queries do the systems differ. You sample this difference correctly. Again, tons of research going on there. You send this difference to the human judges, and you know exactly which one is better, by how much, and most importantly, what are the failure modes? For which queries did your search results decline in quality? And what are the successes? What are the new wins? What are some things that you did not cache before and are caching right now? In fact, I might be biased because that's my professional life trajectory. But I think there are many people like me who would say that we first used the term A/B test for search results, for relevance results. And only then this term was caught up and hijacked by growth hackers. So now A/B testing for most other people today means stuff like we're going to try 10 different front pages, or we're going to try 16 different front pages because I have 4 features and 2 power 4 is 16. Let's see which ones work better. Like feature 1 would be like changing the font size of the caption. Feature 2 would be putting a bigger picture of your avatar next to you. Feature 3 would be 2-step, not 3-step sign-up process, stuff like that. So that's what is commonly referred to as A/B testing on the web today, on the web and mobile apps. In my mental model, A/B testing is first and foremost comparing different ranking functions against one another, finding the inputs on which they differ, finding the minimum set of the inputs where they differ the most, examining these results manually, likely using human labelers, and then making the decision of whether we are doing a good job, but potentially replacing the old version by the candidate version. This keeps turning into my story, which I think is fine too. So I insist that search and relevance and ranking and newsfeed generation are a lot more similar than you think in terms of how you solve this problem. And I hope I'll be able to convey this message over the next few slides. So yeah, building a ranker machine learning problem. I almost feel like we shouldn't talk about this in the context of system design, because it's a lot more about like algorithms, research, and machine learning. On the infrastructure side, yeah, I think what you can mostly win is finding ways to do more computation on the edge. So ideally, your final reshuffling, resorting of the candidate results will be fast enough because all the data is there. You just need to compute a few small functions. Whereas most features, most components, most inputs to this machine learning model application, model inference, will be computed by the index nodes, index leaves. And as I mentioned before, that's of course where the difference between search and recommendation is the most striking. But again, the more machine learning powered your system is, the less this difference becomes with respect to system architecture, because it's just a different weighting of features for your ultimate penalty cost function. So yeah, from the system design standpoint, number one is of course do as much work at the index nodes as possible. And as I mentioned before, if you're doing request response up, down, and back up, you probably would win a lot by replacing this by request stream, so that you can start your computation when the data is only beginning to become available. From the system design architecture, it's not really a system design argument. It's more like architecture of the software plus the people who work on the software. So, but once you combine these two, it becomes extremely clear, at least to me, that whenever you have multiple people working on effectively the same ranking function, the more granular your system is, the more like plugin architecture it supports, the easier it is to separate work, so that different teams can work on different pieces. On the one hand, they don't step on each other's toes, so they can work together without having to constantly sync up on, hey, can I touch that? On the other hand, you can always you can take 10 teams, you can take their results, you can take any combination of their results, and you can evaluate it as the candidate next ranker and see which one wins and then ship it. The system architecture point to be made here is what Rahul asked about at the very beginning, about index of dates. So I'm fairly positive it's safe to say today that there will be a different data and code path for high frequency queries. A famous example here, I think the most, not to say famous, but the most widely cited example here is Twitter, when they first said, hey, we're going to write each tweet once, and when you generate the feed for every single user, we're going to just query this database, select all tweets from the people I follow, order by time, descending. This worked at the beginning, and then they realized that the fan-out factor is huge, right? Because even if 99% of your users have fewer than, let's say, 100 followers, I think the median is like 70 or 50, the distribution is quite skewed, so there will be a few users who are followed by millions of other users, and then suddenly it's extremely ineffective to run this SQL query. So then they moved to like pre-populated feeds. So instead of the normalizing the data towards, I'm going to store each tweet the user has written, the user has created as a content creator, I'm going to keep the pre-populated lists of tweets that other people can see. So if I have 50 followers and I make a tweet, it goes into these 50 places. And it's somewhat faster with respect to rendering the feeds of those people. And then ultimately they went back to the hybrid model, where for most people they use the latter approach, the second approach, where you populate those, once you tweet and you have some small number of followers, small as in reasonable number of followers, you put your references to your tweet IDs into their feeds right away at the right time. But for the users with tons of followers, when the fan-out factor is huge, what you do is you keep those extra data structures, extra servers, extra nodes, extra caches of, hey, if Lady Gaga tweets and you follow Lady Gaga at your tweet construction time, at your tweet creation time, we're going to look at whatever was pre-populated into your tweet by people you follow with a few followers, like your friends and family, and join this list with tweets of the celebrities you follow, because that's the best of both worlds. The same approach, yeah.
Since you brought this up, I was reading that with Twitter, they save only probably in the last 1,000 or 2,000 tweets for your feed, and if you scroll through this, beyond that you cannot see anything. But Facebook, on the other hand, has infinite scrolling. Because you spoke about fan out, I imagine most of the times when I'm on Facebook or Instagram, the feeds I'm getting are from some cache. But if I exhaust that, what do you think happens? Once the cache is exhausted, do they run this massive SQL query and then they construct the next feeds for me? How does that work?
I was tempted to put sorry, I couldn't catch your last phrase.
That is off the topic, I know that, but since you brought up a fan out thing of Twitter, I'm asking this question.
It's not a topic. It's actually extremely related to what we're talking about, I think. because from the system design perspective, that's exactly the failure mode of this approach. Well, my opinion here is that the problem is bloated. It doesn't exist. There's no understanding on this planet today what exactly constitutes infinite scroll. It doesn't it really doesn't work. If you think about it logically, infinite scroll should not be down but up. So you load your feed, you scroll down, but then if you took 5 minutes scrolling down, you're at the end of the feed. What you want to see is what new content was added while you were away. And in the modern UX, this problem cannot be solved. There's people are trained to have some infinite scroll going down, even though it's not really a scroll. It's something weird. In practice, this problem doesn't exist by itself. In practice, there are just two different browsing modes. You want some few results quickly, or you're a special kind of user. In the case of social media, you're a user who's super bored and you spend 10 minutes scrolling down your feed. In which case, of course, the system would see that you're still scrolling through half of your cache. So let's put more stuff into your cache back then. I can guarantee it's going to be a separate algorithm, separate service, separate component, separate cache for you at this point. There's just no other way. It's just, I've learned this the hard way. And in fact, pagination is also unsolvable for most cases. If you have a search query to a search engine and your first page is what's optimized for. Second, third, people sometimes go there. Whether something exists on the 11th page, I have no idea. In fact, I would argue that if you run the same query in 2 different days in 2 different computers with 2 different personalized settings, your 5th and 10th search results page would be entirely different from these 2 cases because nobody cares about those. So yeah, infinite scroll and populating this feed, it has a lot to do with the last bullet point on this slide. So you have this index that serves index plus relevance, the happy path. That is where the juice for the business is. This is what's most optimized. But it's by far not the full system. And then you have a tons of constellation services next to it, which handle corner cases. Celebrities that have tons of followers in the case of Twitter are one of those corner cases. News events, in terms of if it's a blogging platform, microblogging platform, if some events are unfolding right now, if there's a forest fire and people are trapped, it's going to be a separate service that handles it because it's optimized for high frequency updates and a lot more reads than writes. If suddenly a lot more people are refreshing this page, there's a special service that would update every one of these people. Adult content gets tons of clicks for no good reason. I mean, it's a good reason, but it still gets disproportionately many clicks compared to what you would expect for relevance metrics. So it's a separate service. Privacy-related data, such as, so if you're in Europe, you're subject to GDPR. Maybe you have a widget on your page that shows you weather at where you are, but you also have the widget that tells you have a flight in 3 hours. It's time to call a taxi to the airport. This would be different services. So it's in my model of the world, it's healthy when a big product grows. It's healthy that the complexity of these constellation services quickly outweighs the complexity of the core service. But from a system design perspective, in terms of what we're doing here, I think it's a lot more fun to focus on the core service because that's where problems tend to be more self-contained, more computer science pure, more mathematical. So yeah, it's important to know that this constellation has to exist, and it's really hard to manage. But it's just a different conversation, I think. Yeah, so as long as you have a separate service, you just have a load balancer that talks to that service too, and then joins the results. By the way, it's always the case these days that joining the results from different universes is a lot harder than ranking the results within the same universe. So it's a hard problem by itself to rank search results, for example, if you're a search engine. It's a hard job by itself to rank job postings, recommendation, friend recommendations, cat pictures, memes. By the way, memes are horrible. Memes are a separate universe by themselves. They are as bad as adult content with respect to traffic they generate, but they're not adult, so you can just filter them. And from what I know, every single large company that deals with tons of traffic has special policies, special teams, and special services to deal with content that looks meme-ish. because the the common understanding in the industry is that not to say memes are bad, but there's a healthy fraction of memes and an unhealthy fraction of memes, and if you leave stuff to its own devices, it's going to get to unhealthy very quickly. So yeah. Yeah, I guess this was sufficiently covered for this particular slide. Well, I think it's the last one. So I promised to talk to you guys about what actually is different between search and recommender engines. This is the slide where I was tempted to add this note that you asked about, that infinite scrolls, infinite feeds don't exist. So yeah, as I said before, search is a lot more about query augmentation. A lot of search engines, I think the trend as of about 5 years ago was that every single major search engine, they made a huge announcement that, hey, we have improved our ranking algorithms, ranking procedures. And surprise, you can now get search results of documents that are a good match to your query, even though they contain 0 words on the query. This was branded as a huge success. In practice, well, yes, neural networks do have something to do with this success, but it's a very moot point, because in practice, far before neural networks became widespread in retrieval and ranking functions, again, as I said before, both query space and document space are bloated. So if your query space contains some word that has 10 synonyms, and they are commonly used as synonyms, as long as your search index is word-based, and most of them are word-based, chances are that by the time your query gets to the index node, it's a big OR on top of the actual query that return me all the documents that contain not just the word vehicle, but also the word car. It's just pointless to not do it. And you can do it at the node level as well, like at the actual node, at the actual filter set retrieval. You can also do some quick query augmentation if you wish. So all this is being done for like many years. So the argument that our search engine can return documents that are super good match with 0 intersection on the query terms and document terms, well, yes, so what? At the same time, I think in the recommender engines, this is I'm going to make a big point. It might be hard to follow, but once you do follow it, it makes a lot of sense. So every single search engine has what is called static ranking. Think of PageRank as the first approximation of static ranking. Static ranking is just, if document A ranks above B in static ranking, then on average across all possible search queries, document A is more likely to be relevant than document B. That's it. So with other things being equal, prefer A. True statement but pointless. The statement that is true and not pointless is that in the order in which the index leaves return documents, you might want to sort them by static rank, so that what is more likely to be relevant gets sent to the machine, to the node that performs the ranking sooner, so it gets more preferential treatment, which is only fair. So static rank kind of has to exist in the case of search results. At the same time, when you think of recommender engines, in a way, it's all about static rank. There's no query. If the system knows nothing about you, it should show you, I don't know, 5 movies to watch, or top 5 restaurants in a certain location. Well, if you think that it applies some model to pick this top 5 at query time, it's not how it works. If you're a user who's going to the front page of some like TripAdvisor, trust me, they have this page perfectly optimized, precached, manually selected restaurants and travel locations and like flight packages. But in practice, it's hardly a new user with no data, like with no context attached to them, that is coming to this service. In most cases, there is some context about this user. In most cases, we at least know who they are. We know their geolocation. We know their time of day. We know their browser version or device type and ID and stuff like that. Battery level, if you wish. So all these are signals. All these are part of the query. They don't translate to query terms per se for the index, but they all would eventually play in this final re-ranking stage. The trick is how to make use of these queries, make use of these second-order signals at retrieval time. And as I said before, when it comes to search ranking for like web search, if you know nothing, just return top statically ranked results. Or if you don't have much signal, prefer whatever is high ranked statically. But when it comes to personalization, for example, if you think of how collaborative filtering works, if you think of how matrix factorization works, ultimately you would have, like, as a super high level approximation, you would have like a n-dimensional document vector, n-dimensional feature vector, n-dimensional query vector. You would take a dot product and see where it's maximized. So it's like the angle between two vectors in the high dimensional space. The more collinear they are, the higher the chance they are related to one another. So in a way, mathematically speaking, you can think of recommending content to you as think of like an n-dimensional hedgehog. Think of a sphere in 3 dimensions, and each point on the sphere is a document, like a movie to recommend, a restaurant to visit, and like there's an arrow pointing from the center of the sphere to every single point that corresponds to some piece of content. Instead of 3 dimensions, think of like 50 dimensions. So the problem of recommendation becomes: here's my preferred vector. Find of all the space of documents you have, find the ones that are as close to me as possible in this multidimensional space. But the thing is, there's curse of dimensionality, and suddenly, even though the space is like 100 dimensions large, effectively there are only a few dimensions, because restaurants, people, movies, content tends to get clustered across just a few axes of interest. If you want to do collaborative filtering at scale with all these dimensions, what you would do is matrix factorization, usually via single value decomposition, and you would find some dominant directions, like prevailing components of this vector, of this space. You can use each of these components as a direction to statically rank documents. So if it's like food recommendations, if you just apply matrix factorization to all this huge matrix of restaurants and their properties and guests and their property and their preferences, you would find a few dimensions such as spicy food or Asian food or like hot food or street food. Once you have these dimensions, they would just arise naturally from the mathematical procedure of matrix factorization. Once you have these vectors, this is like a preferred arrow direction in this multidimensional space. So you orient your hypersphere so that this vector faces up, and you sort all the restaurants by like the resulting y coordinate. So the highest first. So as in like the perfect match would be like this is the center of your sphere. This is the vector going up. Perfect match would be a dot product of 1 because these two vectors are extremely close to one another. This is like 0.5 because this projection is 0.5. So you just sort them by whichever ones are the closest to this vector, which becomes a static rank. And then suddenly, in order to find the closest matching points, restaurants in this space, you have the vector for the user. You have some idea of their preferences. You can quickly project it. It's just a mathematical transformation. You can project it onto this matrix vectorized space. You have the key components in this projection. So pretty much you know that this user prefers spicy Asian food. Perfectly fine. Instead of going through all the documents, you can look at the top few documents that are in the category of spicy food and top few in the Asian food and then merge them. So you can think of them as multiple possible functions which become your static rank functions. And then each index node, each index leaf may well contain different orders of documents sorted by different preferred ranking functions. And then in memory, during the query time, they will perform like a merge sort, like an in-place merge, and they would return you the top few documents that are an extremely good approximation of what you would get if you take all the documents, take this dot product, and resort it by the resultant dot product and pick the top few. I think my explanation was terrible, but the point is once you connect the dots, it actually makes a lot of sense. Yeah, what else? I think that's it. It wasn't too long.
I have a question regarding this kind of tree-like architecture of the whole index infrastructure. In the easiest in the simplest case, we have a node on top which blows up a single query to some number of them, and then sends all these queries to the shards, which store actual data and pre-compute as much as possible up to the CPU bound, and then they return the results. And here we get merge of all the results and return. I suppose that is the easiest case. And when we speak about the practice, how many layers in between the highest one node and the bare bone shards we have additionally?
I'm tempted to say 0. In practice, I think
wow.
you can almost always have a 2-layer architecture that is good enough. I mean, you can always, if you have 1,000, 5,000, 20,000 leaves, you can always have multiple like first order rankers, and you can just waterfall over them in like load balance over those machines and be cool with that. So it's not about the number of levels, it's about how much work can you outsource so that you can reuse the results, so you can use some clever caching. But I think with respect to search and relevance and ranking and recommendations, this very problem has a better solution, which is separate queries into like high frequency and low frequency, and just keep chipping off parts of this pie, taking the high frequency requests out of the picture.
And does it make sense to make some intermediate query results merging, or it's not that much that we can just do it in a single run on a single machine?
Your mileage may vary. There's no magic bullet here. My instinct tells me that so there are two fundamentally different problems. One is compute as much as you can per document, not looking at any other documents. The other one is comparing documents to one another. For example, you may want to make sure you don't show similar pieces of content in the same feed. Like if suddenly all your friends are posting pictures from the same family gathering, it's okay to show you a few, but even if they're all super relevant, you probably want to splice something in between those. You don't want to spend the first 2 minutes of scrolling Facebook seeing the pictures of the same family reunion. So at this level of re-ranking, you need to apply functions that already see this whole, or at least a large fraction of the search results tree. So it sounds like search as in retrieved results. So the point is, at some point, either you can push the logic all the way down to the leaves, or you cannot, because it has to have access to everything. The man in the middle step, the intermediate step, would have the benefit of none. So if you need to augment those results by some features from other like machine learning equipped database, so you need to just extract some numbers and then compute something, maybe use a neural network to then later use these results of this computation as at the highest level part, then yes, then you can have an intermediate layer that does this computation. But this would again be something you could push to the leaves, right? In theory. So it's also about pushing code to data. If it can be done on the leaves, but leaves are too busy, you have another cluster of machines that are closer to the database that they have to go to, and the query goes to the leaves, to these machines, and then back up for the final re-ranking. But it just doesn't seem plausible to me to have a service that re-ranks the second page of search results.
I see. Thanks.
One thing I wanted to say and forgot is, it's in the slides, but I didn't use them as always. I'm usually the guy who's extremely pro reproducibility of results. I think it's extremely important in computer science, in system design, that you can run the same query and expect the same result. Just because if you don't have this property ingrained in your system, you're guaranteed to have some bugs that are super hard to catch, in my experience. At the same time, when it comes to search ranking, I once entered a huge argument where I was trying to say, hey, let's keep it reproducible, but ultimately I conceded. I think it was a good idea to do it otherwise. And it's the idea on when to stop this stream of results from the node, from the leaf of the index. So it's one of when you need to merge results from the node leaves, from the index leaves. Once you take the step from request response to request stream. This stream is potentially endless, right? So at some point you need to stop this stream and saying, I'm going to send up like out of 100 documents, or I'm going to send up the documents that have the score of at least something by my own internal metric. You do get reproducibility for this, but at what cost? It increased latency for the end user, but we know that the latency is more important than precision. So the argument I was arguing against, but ultimately I think it's a good argument, is that the answer to the question, when do you stop sending documents back from the leaf to the ranking entity? This question can be answered in a very simple way. Send for this many milliseconds. Like once you exceed your timeout, stop. It sounds remarkably wrong because suddenly the machine is slow, the garbage collector kicked in, and you have a different search results set. But it's actually okay in practice because it's better for the end user facing metric of having good enough results quickly.
I have a question. When we were talking about storing the indexing, if I understood right, there are two options: log structure merge tree or key value data store. Am I right?
I was trying
Or
to.
it's about this. It's all about the same.
I was trying to connect the dots between two universes. I don't think I've done a good job. So it's always going to be key value. Log structured merge trees is the idea that instead of updating this key value on the fly, you just rewrite the whole thing and hot swap them at some point. So the index itself is always key value. The question is, do you optimize it for potentially quick updates? As in, is it like a red-black tree, or is it a sorted list which you can just update once you have enough updates for it to be worth updating?
Oh, makes sense. And another, actually also relevant to this question. I also read that sometimes it is used document store like MongoDB for such tasks. What do you think about it?
I couldn't catch the question, to be honest.
So the question is about storing the indexes, and as you answered me that it is almost always key value store, and it makes perfect sense. And another question is, I read that sometimes it is used document values document store is used like MongoDB. And my question is, what is your opinion about it? What do you think about it?
Okay, yeah, that's tricky. I think to answer your question, let's first establish the difference between like a database index and a search index. Like you can think of Mongo is a document store that is usually contrasted to a database like Postgres. The idea being that you have a RDVMS on the one hand and a large-scale document store on the other hand.
Oh, I see.
So if you want to search documents in MongoDB, so first of all, Mongo stores documents, not small keys. If you want to put the inverted index into a key value store, you probably want to use Cassandra. I mean, it's going to be terrible. Lucene or Solr are better. But if you as an exercise, if you want to like pick a database to store the inverted index in, Postgres would be a bad idea. Cassandra would be a bad-ish idea. Mongo would be a terrible idea. And when it comes to the actual search index, so I mean, Mongo is actually, I think one of the first query languages was specifically MapReduce-like. So the claim the company, the architects made was, we don't care about like SQL-like queries. You can run any MapReduce. You can write a mapper function in JavaScript. We're going to apply it to every single document. Write a reducer function. And if your code doesn't contain bugs, we're going to give you the result of this computation. This works, but it's slow. And if we're talking about, hey, I would like to be able to search these Mongo documents by this string field, effectively you're telling Mongo, hey, build a secondary index, which would be a key value store, like inverted index of textual words here. You're trying to tell Mongo to have a small Lucene index within itself by some key, or by some field. I'm not sure if it's possible or not. I'm not a Mongo expert. I would not be surprised if it's just possible. I would not be surprised if there is a plugin for Mongo that is like third-party, proprietary, or even open source. But effectively, once you're there, you're in the mode of designing Lucene or Solr within Mongo, which is the same weird problem as designing Lucene or Solr within Postgres. You just don't do it. If you have a large volume of data, use Lucene or Solr, or design it from scratch. And if you need to search within the document store, don't pretend it's an engine to store the inverted index. It's a document store.
Yeah, same thing.
Yeah, when I think about it, Dynamo would actually be okay for a document store. So Postgres is bad, Mongo is bad, Cassandra is okay-ish. Dynamo could be a good first approximation of what the database should look like, what the data store should look like to store your inverted index with the ability to query it quickly. So like if I'm challenged with hey Dima, can you build something that is faster than Elasticsearch using some existing database? Even if it's possible, I think it is possible. Elasticsearch is slow. I would certainly not do it in Postgres or Mongo. I would not do it in Cassandra. But if I'm not allowed to write my own, I would probably try Dynamo because it's probably the closest I know that can handle both high performance and certain kind of read like query throughput. But it would be like trying to use the wrong tool for the job.
Thank you.
Yeah, that's what I keep talking to people about. That effectively, like in the modern world, we like talking about microservices, and we have this elk stack, right? But fundamentally, within a database like Postgres, if you say, "Hey, build a full text search index on certain column," effectively you're spinning up a microservice called Elasticsearch within the macroservice called Postgres. Logically, it's the same thing. It's a different boundary separation between nodes and services. It's all in one machine after all. So it's the same thing over and over again on this planet. We're doing it in Kubernetes and in the cloud these days, as opposed to trying to use RAM and disk effectively and normalizing the data because disk is more expensive than RAM back then. Alrighty. Shall we call it? Maxim. But you are muted. You're still muted.
I'm sorry, still?
Yeah. This works.
Sorry. Yeah, just wanted to ask something, not exactly system design-ish, but don't you think that actually using like personal data for searches or for recommendation can it can show a good result for the user, but ultimately for the population, it can be bad, like creating echo chambers and only showing you results that confirm your bias. And so maybe it's sometimes it's more profitable to use to ignore personalized results and show everybody the same.
Ethical questions. I have a standard boilerplate answer to ethical questions, which is extremely simple. I believe in technology. I think if the user wants to have a service that is free of this bias, then we should offer this user to have a checkbox set. I want to have certain technology disabled for me or enabled for me. I hope to live all my life in the world where, as an engineer, I don't have to make these decisions. It should be a product decision. As a technologist, I want to make sure we build technology that can solve problems, including this one. So yeah, on the product level, we can have a real conversation. Is it a good thing to do? What should we do? Like if I'm the CEO of Twitter, what should my decision be with respect to how do I bias algorithmic feeds? How much of my revenue bottom line am I willing to hurt because I believe it's better in the long run my company and for this human species. I'm not a CEO of Twitter. I don't plan to be one. So I think I haven't I think my ethical responsibility is to talk about this in proper terms, but I'm trying to refrain from value judgments of how the world should work. I'm pro-market. The world should try different things and see which one wins in the long run, not just in the short term, like revenue gains and popularity gains, but also in the long run of different types of information spread sharing systems competing with one another on a large scale. Yeah, I think that's a good way to end it. Thank you, guys.